Hello, everyone listening. Welcome to another episode of The Circuit. I am Ben Bajarin.
Hello, world. I am Jay Goldberg.
We are very excited with today's guest. We are joined by Aart de Geus. He was the founder of Synopsys. I heard you speak, Art, at Intel's IFS Day and was like, we got to talk to this guy because A, it was super insightful, and B, you had tons of unique insight about the semiconductor industry. So very happy to have you on. Why don't you quickly give a high-level view of yourself in case anybody doesn't know who you are? Just quick intro.
Okay, well, first, pleasure to be on your show. And it's always great to talk about our field because it's such an exciting field. And I've had the good fortune to be in it for a bit over, I want to say, 45 years or so, all the way from school. And for the last 40 years have been essentially on a pathway that resulted 37 years ago in starting Synopsys. And Synopsys today is a company that provides the design tools and the major IP blocks essentially to most of the chips in the world. And of course, that's been an amazing journey, and just holding on for sheer life in that journey has been the hallmark of what it's all about.
Amazing.
So, I'll kick it off. Let's just pretend I haven't worked in the industry for 20 years and I know nothing about EDA.
Okay.
Could you explain to me what EDA is? Let's just imagine I'm a 5-year-old because that's pretty close to my understanding.
Well, okay, we are working at the same level, and so that works. Maybe I was 7 years or so to doing the first circuit, and at that point in time, it was really a battery and a little lamp and maybe an on-off switch. It would have been better if it was a resistor, but that was the first circuit. And what EDA was really an ability to see how this works without having to build it, without having to connect those things on a computer. And the first really worthwhile program that did that was the program SPICE. And I'm particularly enamored with SPICE, not only because still today it's the leading circuit simulator in the world, and you can do very, very complex circuits on it. But as a little side note, it turned out that my academic advisor when I came to the US is a fellow by name Ron Rohrer, who's the person who started that program. And of course, in the early years, I had no clue who he was and had no clue how important SPICE was. But through that connection, I got to know many of the early participants and founding fathers and mothers of our industry. And so that small circuit is a good example of where it starts. And so in general, what computer-aided design, which is what it was called at that time, is try to mimic certain things on a computer and then tweak the knob, so to speak, tweak the numbers, change the resistance, change the voltage, and see what happens to your circuit, and does it do what you want it to do. Now, today, in very different contexts, we would call that a digital twin. In our field, we call that, of course, a simulation. And from simulation came then many other products. But that's really, I think, the starting point for computer-aided design.
So one thing I think is super interesting, right? You've been around since very, very early days. You've seen a number of inflection points to this industry in terms of obviously how transistor designs changed, how the functional design of those chips changed, right? The way that we've moved to integrated now, and then to some degree some disaggregated designs. In your view, looking back to where we are today, like what were some of those key inflection points, milestones, innovation moments that existed and got us to where we are today?
You realize that question is like so unbelievably broad because there's the manufacturing, there's the design,
Sure.
There's the automation, and so on. But we tend to forget because it's so obvious that the single biggest inflection point was the shift from circuit design, analog mixed signal design, to digital design. And one cannot overstate how unbelievably powerful that simplification of simulation of how you think about the world into ones and zero. Only two things, a 1 and a 0. You could say, well, we can simplify more, have only zeros, but that would be pretty boring. But ones and zero allowed us to bring a degree of complexity to things, and a degree of automation and computation that has, as we all know, followed this law of scale complexity referred to as Moore's law, which at some point in time in the mid-60s was stating as it would double every 18 months and then every 2 years. And while today it's not moving at that same speed, it is still moving forward with still smaller transistors, still embodying the digital function. Now, by now, this is so refined that each one of the digital functions is really a very sophisticated analog circuit to make it work. But we can still think in ones and zeros, and that is undoubtedly the biggest breakpoint. Now, if you look at the field that I've been in, which is, of course, providing the design tools to help this progress, we were very fortunate because when Synopsys got founded, which was December '86, we had a technology that had been developed in my team at General Electric called synthesis. And what synthesis did was not just assist you in design, it would actually replace certain tasks and automate it. And I consider the combination of synthesis on one hand, of place and route, which was the physical placement, as the word says, and the connectivity, the routing, that those are the two things that really made the passage from computer-aided design to electronic design automation, the emphasis being on the word automation. And it's really the automation that became the key ingredient for success of this unbelievable digital exponential rate of change and growth. Now, over the years, and so we're talking now, '86 was the beginning of that. Over the years, there have been other waves, of course. There have not only been waves in terms of how circuits have changed, including the very nature of the transistor. And you may remember, it now feels like already a long time ago, but these flat planar transistors, at some point in time, somebody said, no, we're going to go do FinFET, vertical transistors. And the number of people that said, this will never happen. These are wobbly, they're too thin, they're difficult to manufacture, and. And here we are. Now even automotive is using some of those. And so never say that something is dead in our field. Because, yes, the science may say there are some hard limits, but the engineering knows how to work around it.
Yep.
I want to dig into something you said. Did I hear this right? You said that today's digital circuits have gotten so complicated, digital transistors have gotten so complicated that we're back to modeling almost analog circuitry? Did I understand that correctly?
Oh, yeah, but that actually started much earlier than you think, because even when I was at General Electric, you would think of a circuit as, here are a bunch of gates, NAND gates, NOR gates, inverters, and there would be wires in between. But already then, and actually that was the very first thing I did as an employee at GE, was to help develop a program that would compute delay. And delay was not just a wire, it was like a resistor and a capacitor, a capacitance. And so, that is an analog thing, because that says, over time, the longer you make the wire, the worse the signal at the other end, right? And of course, the nature of digital is that it restores the quality of the signal as you come out of the next gate, and so you can do the next jump. Now, that has, in itself, connectivity has become much more complex. But if you look at transistors, and Synopsys here too is the leader in providing the tools for it, the design of those transistors is done with so-called TCAD, technology computer-aided design, where we look at three-dimensional representations of every part of a transistor and look at the internal fields and the flows of electricity through that. And just to give you a sense, the thickness of a gate in an MOS transistor is now measured in very small 8 or 9 layers of atoms. That's how deep this is. So it's atomic level simulation for very small parts in order to just know how this is going to work.
So help me out a little bit, because I think when most people, or at least when I imagine EDA tools, I always pictured like a CAD tool, like an architect would use to lay out a floor plan of a house, just drawing a bunch of boxes and things connecting it. But I know now that it's more complicated than that, and that sort of layout is just a small part of the function that EDA tools provide. Can you just sort of walk us through what goes beyond just the layout? What's in an EDA tool that designers use?
Yeah, you know, I actually love your analogy of laying out something just like you lay out a house, because that is actually called place and route. You place the rooms and you route the hallways or how they're connected with each other, right? And so it's a very important perspective because it's sort of the physical, literally called layout of how the chip's going to look. But that chip is not just a bunch of transistors connected. It is very large blocks. It's a very hierarchical structure. And so today, just by the way you would do it in a lot of industrial design of houses, you wouldn't design all the details of a kitchen. You go to the catalog and you get the whole kitchen with all the kit and caboodle, and there it is. And these are standardized and ready to go. And so you design very fast. So it's these large group. Now, the other thing that you have to realize is the analogy of designing a house is quite good, but by no means complete, because the way you have to think about a modern chip today is more like an entire hotel. Actually, more like all the hotels in New York and all the streets, and everything runs, and there's not a single car that has an accident. And that's the complexity we deal with. And I always marvel when I think about it, especially when it doesn't work in a hotel. How do they manage on 50 floors to make sure everybody has hot water when at 7:30 in the morning everybody takes a shower? Well, that's called power distribution, right? You have to compute all of these things as a function of the behavior of the chip. And that is what EDA does. There are many, many tools. For starters, they look at functional correctness. So a good example for functional correctness is you have your hotel, except with 3 of the rooms you forget to put a door. That is a bit of a problem, but that is also something you could check for, right? The door checker. Well, we have a zillion of these checkers on how to do the layout. We have many, many checkers to look at the quality of the signals. And most importantly, we need to verify the functionality. So if you do a multiplier and it multiplies most of the time except when a 7 is involved, then you have a functional error. And we so often forget that because in our field, when we talk about improving circuits, there are 3 letters that always come up: PPA, performance, power, and area. But the more fundamental one is function. First, make sure it actually really does what it's supposed to do. And then the PPA is how it is doing it. How fast is it? How low power is it? How small can you make it? Because the smaller, the better, the cheaper it is to manufacture, for example.
I do like the hotel example because, again, right, that talks about the way in which transistors are being designed, right, so vertical stacking. But I'm curious how you think about, one, I followed a lot of the announcements around some of the AI kind of aided design, right, that you guys are doing from a Synopsys standpoint. But when you think about that, right, that there's a lot of complexities in some of these new designs on the top of some of these things we're on the cusp of, like ribbon FET transistors and backside power. Do you see kind of all of that also going together in that those things become equally as necessary, or in this case, right, the AI design tools for perhaps this step function in transistor and power delivery that we're about to see?
Sure. So let's segregate 2 things, because you talked on one hand on capabilities and features that a circuit could have, on the other hand on the tools and the automations to make them happen. And so on the tool side, and we didn't really go through all the breakpoints, but we talked a little bit about these early tools. Then came the automation wave, the digitization, and then of course the tools got more and more complex. There became more and more tools together, and gradually the need for the tools to work well together, meaning to not only to connect from one to the other, but to actually not have one tool push the design in one direction for the other one to correct it in the opposite direction, so to speak. And so it was only as we mastered the skill to do that a new set of optimizations suddenly became possible. And they became possible because the computation was sufficient to finally give AI something meaningful it could do. And if I can characterize from my perspective, the one thing that AI could do that deductive reasoning or standard computation was not so good at is pattern recognition. And when you think about optimization of any problem, there's always two ways. One is look at the numbers and see which ones are off and try to optimize those. But the other is look at the patterns where a certain pattern is more likely to do well than another pattern. And the minute I saw that the Go game had been mastered, what they said was what was different than chess. In chess, it was essentially look ahead. How many moves can you look ahead? And if you can look more moves ahead than the human, well, you're in a good spot. With Go, there were so many potential moves that you could not do that. So instead, it won by starting to recognize certain patterns that were more likely to win, and then essentially statistically try to find those and follow a path that way. And the minute I knew that that was possible, I realized that for our field, it would be the same thing. And so then came a whole wave for each one of our tools to say, well, of course, we've optimized the best we know how. Now let's see if we can use pattern recognition to see if there are additional optimizations. And the answer was definitely yes. And the tools got easily 20% better during that time. But then came the next step, and that's the one that I'm really proud of, because Synopsys has been absolutely an AI pioneer in that direction. And that was, can we take multiple tools that typically is a flow of activity that you do in order to design a chip and optimize that? And that was way, way more complex. And the first time that we saw real results was actually in late 2019 already, where we saw, hey, we can do circuits substantially better and much faster than humans could. And today, some 4 years later or so, we have well over 300 production designs that are being done with that. So it's grown very, very rapidly. And now, of course, with the Gen AI wave, there's a whole set of additional assistants or co-pilots that can be mapped around this design flow. Now, this is just in time because there's a massive other change happening in circuits and in chips in general. And I'll talk about that in just a minute. But that's sort of been on the design side. Now, you mentioned a couple of capabilities. One was backside power. Backside power is super exciting because for many, many decades, there was a chip is sort of a substrate of silicon, and then you build stuff on top of it or into it. The very fact that you now can think about attaching something from the back and actually drill holes, they're called silicon vias, essentially stairwells, if you like, and bring the power in that way is great, because now you don't have to have that power distribution come top down, right? And it's in a weird way not all that different than in the US. A lot of power is distributed via wires that go all over your head, except for places where they put it under the street. Well, if you can put it under the street, you don't have the poles, you don't have all kinds of other issues. And in the case of electronics, this is way, way more meaningful because space is absolutely at a premium. So you come from below. And so every time there's an invention like that, all the tools have to adapt very fast. And initially, you have to think differently. Well, now you have to push things aside. You have to drill holes. The holes are much bigger than the lines. There are many issues to deal with. But that is what automation is all about. And here, too, we drive absolutely the state of the art of this.
So
Fascinating.
I have a question going back to the AI to Copilot. We have a lot of designers who listen to the show. Do you think we will get to the point where generative AI EDA tools can entirely replace the designer? Or maybe a better way to ask that question is, what are the things, if you were talking to someone who was just starting in the industry and wanted to be a chip designer today, what would you tell that person to do? What skills should they learn to future-proof themselves from being automated away by AI?
Well, first I'd like to answer it with what happened about 6 months after we had started Synopsys, because we had the benefit of having a well-honed preliminary system from General Electric that we could use. And so we would go to customers and ask them for a design they were working on, and then pass it through the synthesizer, and literally in a few hours come back with something that was 30% smaller and 30% faster. Power at that time was not a consideration. And they would look at that and say, well, it's impossible that you can do that. And then would go away for a few weeks checking and checking and checking, and then they come back and say, this is amazing, this is really powerful. And in that context, there were maybe 3 or 4% of the engineers that essentially were worried, oh, you're taking my job away. But the other 95% thought, this is great, now I can do so much more. And I think right there, that is sort of almost a foundational attitude towards technology. Yes, the technology can take certain things away or make it so fast or so simple that you don't have to do them. But it's also true that if you know how to use that technology, you can do fantastic new things and make progress in your own way. And I think everything we do right now is in that category. And in a minute, I'm sure we'll talk about the whole switch from classic Moore's law to SysMoore, which is systemic complexity exponential. And there are so many opportunities in that. These type of tools are an absolute necessity to be able to move forward. Now, in general, having an open mind to change is a necessity when you live on an exponential. And exponentials are really sort of the most amazing, mathematical functions, I think. The mafia discovered that a long time ago, right? Which is, hey, I give you a really good loan, 2% per day. 2%, per day. Yeah. But that's an exponential. That sucker moves like crazy. And I predict that we see another 2 decades of that, not in the classic form, in a new form. But there's so many new opportunities out of that being open and willing to learn from the past, but also imagine the future, and find those places where tools can assist you, and find those places where your own imagination, intuition, and drive can bring new opportunities.
Interesting. So maybe talk a little bit about the relationship between design and then foundries. When you're looking at some of the intermediary that you're playing, not just Synopsys, but obviously designers have a whole host of things that they go to in terms of getting their chips fabbed. How do you think about that, or really what's the relationship between EDA and foundries as well? Because we talked about design-centric points, but what about from a foundry level?
Well, so it's useful to understand sort of the layering of the industry. The foundry is fundamentally the group of people or company that manufactures a design, right? So they get plans of a design, and they translate these plans by layering a variety of things on the chip, and there's a whole set of techniques. They themselves are supported by another layer of companies, which are the manufacturing equipment vendors. Very, very sophisticated people as well. And so on top of the foundry sits the design community, often called the semiconductor industry, and they design a chip for their customer or customers, which are the people that want to run software or do some tasks with it. We sit on the side of this entire picture because we touch all of these people. We need to know from the equipment vendors where the technology is going to go. With the foundries, we provide things that without those, and I'll get into that in just a second, they cannot go to market. Designers are our dominant group of customers, and then you have system houses and software vendors on top of that, and we interact quite a bit with the system houses as well to understand where the architectures are going. And so the relationship with the foundry is absolutely central, because in order to be successful as a foundry, you need first technology, and the technology invariably is characterized by a thing called the PDK, the production design kit. And if you don't have technology, you have nothing. But then you need to actually have manufacturing capacity, because if you can do 2 chips, fantastic, you've proven something, but really you need to do 2 million a month, right? And so the capacity is something very expensive and typically runs about 20 billion per fab today. So these are not small investments. So it's a very capital intense organization. Now, in order for their customers to be able to give them the plans, their customers need these PDKs. They need the basic building blocks. Think of the Lego blocks, the NAND NOR gates, the basic library. They need a library of very sophisticated blocks, such as a USB, any of the other transmission mechanisms that are used, product protocols, I should say. And then they need the tools from us. And these all need to work. If you miss one of those, when the technology is ready, you cannot do any design. So it has to all come together at the same time. Well, given that it takes multiple years to develop those, the foundries and ourselves have to work hand in glove towards arriving to the customer at the same time. Otherwise, nothing's going to happen. And so those relationships are very, very essential, really, for the whole industry to function. And, sometimes also have some stress because, who is late at any point in time is always in debate.
Interesting.
So I do a lot of work on China and China semis. I lived there for a long time. And I'm just curious, there are a lot of companies now in China building EDA tools, domestic EDA tools. Have you had a chance to look at any of them? What do you think of the prospects for another country to develop an EDA industry?
Well, this is nothing new. I mean, for our entire existence, we've had a very large number of EDA companies, not all of which, but many of which we competed with. And so there's only one reaction for us, be it in China or any other country. Our job is always the same: run faster, run faster. Competition drives you forward, and it's not easy to build a good company. And of course, we are very advanced because we have many tools that all intersect and work very well together on the most advanced chips in the world. But never, ever, ever underestimate any competition whatsoever. And paranoia does sort of keep you alive.
Okay, let's jump to the future. There's so many things within this I want to unpack, but let's start, I guess, with some of the things you hit on that I think are a little underappreciated. You hit on this in your Intel talk about the Angstrom era, moving from what we're looking at in terms of just the generic elements of Moore's law. Obviously, we've all talked about it's getting harder. Whether cost per transistor is going up or staying flat, the bottom line is getting the same gains is just much more difficult. So you're seeing lots of approaches of design. But everybody likes to talk about, we still think we see 10-ish more years of innovation here at transistors levels, and what that looks like in terms of new transistor design. So maybe just kind of briefly unpack that view that you sort of shared around how significant this is and kind of how you view this next era, this Angstrom era.
Well, so for starters, pretty much everything you said, you could have almost used the same word except the word Angstrom in the late 1990s, because it was getting so much harder and it was going to become impossible and so on. And then I forget when it was, probably late 2000, mid 2000s, that suddenly, copper came up. And until then, copper was a metal you would never, ever, ever, ever use in manufacturing, because those atoms diffuse easily into the rest, and now you have one big short circuit. Except we found a way with Damascene to protect the chip from it, and here we go. All copper connectivity would change things for the positive. And then, as mentioned earlier, comes this notion of, well, those flat transistors, really hard to get more power out of them. What about we move them vertical, and now we can really pump something through? Except that it's impossible to manufacture, we'll never do that, and so on. And then 10 years later, we're already in the 4th or 5th generation of that, and moving forward. And then comes, of course, now the next category, which has different names, but is essentially aggregating multiple FinFETs together to crank even more power on less area through. And by the way, in that context, we still shrink the most important sizes, which is the gate width. And now we've moved essentially, certainly during my tenure, so to speak, from microns to nanometers to angstrom. I particularly like angstrom, as you know, because it contains the word angst. And so it sets the right tone for the amount of energy that we need to pump into that. And yes, it is slower in terms of the return of investment, but it is not less amazing. And it's not less amazing because it is truly fantastic how both in lithography, and certainly a company like ASML deserves a lot of credit for its ability to have focused those beams to even smaller wavelengths. But also in the other manufacturing side, we have gotten to these sizes. And a number of people have announced that their 2.0 nanometer or 20 angstrom is going to 18 and to 14. And there's sort of a roadmap to get to single-digit angstroms, which, well, okay, what is really small of something that's already very small, right? Right. And so that is continuing. But you can see that it has gotten more difficult at the very moment where the demand for way, way more transistors has gone in the opposite way. And of course, now I zing forward to the end markets that say, well, AI is going to do something in the world. And certainly the amount of computation that goes into that, the amount of transistors needed, the amount of storage, of computation together is going through a massive exponential. And, one of my favorite terms that I use all the time is techonomics. What we find here is that after, in many ways, 50 years plus of technology pushing things forwards, the tech part of onomics, and then out of that technology, you can run software on it and get economic return. Now suddenly, we find that the onomics has gone nonlinear forward and say, hey, the whole world is going to get smart in some way. Intelligence will be pervasive all over the place. And all we have to do is umpteen gigawatts to get to train all these systems, and just as many gigawatts to use them as inference in all the IoTs that are around in everything that we touch. And so now suddenly there's a pull, right? So there's a technology push, and now there's a pull upward, and that suddenly brings a high demand on the bottom part of the picture, which is deliver these systems. And so this is where I like to introduce the notion that we have now moved from the traditional transistor scale complexity to now systemic complexity. Systemic because just transistors will not do it. We have to do other things to get more compute capabilities. And moreover, the impact of the software as being the things that actually drive the essence, that define the architecture, is enormous. And so all of these forces have to be satisfied at the same time. And so here comes at just the right moment a great opportunity, and that opportunity is to start bringing chips way closer together. And this started a while ago by essentially saying, why don't we take two chips and we put them on another chip? That other chip is called an interposer, but fundamentally it's a chip, and we connect it through that chip, and that is really a lot closer than what you can do on a board, for example. And of course this has matured, but now we're going to one-up this by a lot by saying, you can also stack them vertically on top of that. And now we're back to, our 5-year-old doing the design of hotels, right?
Yes. So obviously you're bullish on chiplets, but within this, I think there's an interesting point, I guess, to be made, and I'm curious kind of how you think about this. Do you think that we are, because of these things, the complexity in design, this opportunity to really build much, much more complex and diverse systems of chips, are we in perhaps a phase where we might see a lot more creativity in design from perhaps even more people? Because I'm sure you're tracking and probably provide tools to a lot of people doing custom silicon, right? Look at the hyperscalers. Obviously, Apple does this. We would imagine perhaps others will as well. But everybody's attacking this from a different way. Highly creative, very flexible, sometimes perf, sometimes wattage. But given what we're seeing from a systems design point, I'm curious your take on like the creative element of that. People being trying things they didn't do, or being much, much more creative in the total system approach than we saw in monolithic?
Okay, so it's a wonderful question, and in order to answer it, I want to park a few things. You used the term chiplet, which I did not use on purpose, because chiplet is almost more of an economic opportunity sentence for people that want to provide certain pieces. The first integration is actually not chiplets at all. The first integration is of some of the most sophisticated chips. So massive processing with acceleration right next to it, and massive memories as close as possible, long before these other chiplets, and I hear some analog mixed signal thing is going to drive something, or even some sensor. That will happen too. No problem with that. But the essence is driven by the most state-of-the-art things, because they have the biggest need. You can put some more transistors on that chip, but if I wanted twice as many, I need to have 2 chips. And if I want twice as many, I'd prefer 2.5 times as many. So keep pushing the Moore's law that we talked about earlier, the classic Moore's law. But the systemic, what I like to call SysMoore, is really the notion of now bringing multiple very sophisticated chips very closely together. And for starters, it's absolutely processing and memory around it. Now, processing itself has already subdivided into graphics processor, highly focused on a certain type of software, and of course any form of other acceleration, much of that all going into the direction of be it either AI training or AI using the data in some other context. And so what is so key to understand is a question that I've wondered on for quite a while. Why is multi-die now? Why was it not 5 years ago? Because, why not get twice as many transistors there? Well, for starters, the demand was not as harsh as it is now coming down from this unbelievable economic opportunity of AI. But the other reason is that often people talk about multi-die as, packaging. It has very little to do with packaging. It has all to do with connecting. How well can you connect these chips? And the important thing to understand is that there's a new technique that allows to essentially stack multiple chips by having copper connectors that run through the chip and that you push on top of each other. That's step number 1. Step number 2 is that the number of those connections that you can make has passed 100,000 per square millimeter. Now, if you're in the US, you think in inches or whatever these things are, but square millimeters are really tiny. Put 100,000 on those. Between multiple chips, you now can have an enormous amount of connectivity. And my working hypothesis is sort of exactly what you said. This opens the door for an enormous amount of creativity in rethinking architectures, because it's the same as saying, in those big hotels, if you want to go to your kid's room that's underneath your room, you don't have to walk all the hallway, go down the elevator, walk all the way back. No, you can have now a little stairwell right there where you need it for between compute and data, for example. Actually, you can get 100,000 of those on a very small space. And so the fact that the delays on chip and delays between chip are now essentially the same-ish is the same as saying you have just opened a world of connectivity that is of enormous impact at the moment where the world puts enormous pressure to do something better and faster and sooner. And so for us in our field, we have long come to the conclusion that therefore we need to think in multiple dimensions at the same time. We always had multiple dimensions. We certainly had X and Y and temperature and timing and power and so on. But now it gets way more complex. And there's also one big challenge with that is if you stack stuff that is really potent on top of each other, they're going to fry each other, right? These compute things take a lot of wattage. And so there are technical issues, but the opportunity space is wide open. Yeah. And systemic complexity is what describes this.
Yeah. I think that's been similarly where I land. Just a broad point, no more sort of broad questions, but just a broad point that I think is interesting is I think that there's been a lot less credibility and really recognition of really good architectural design. Now we can look at those competitively in the monolithic era, and I think similar to like you said, I thought we're going to see a lot more of this and really go in ways we hadn't seen because people will take very different approaches for different agendas, whether they're custom people, whether that's the Intel, AMD, NVIDIA, etc. And so I'm just so intrigued by this because, like you said, right, so many more possibilities come up. But to the foundation that Synopsys does, with all those possibilities, you got to really choose the best optimized solution, and that's where it'll be really interesting to see, I think, how everybody approaches this within their product roadmap and their architectural strategy.
I think what you're saying is right on and fantastic. And the challenge for us, of course, is to always be sort of one step ahead in thinking through this. Because if you know what are the characteristics that determine the success of an architecture, then if you're in the ballpark, you can optimize to get better and better results automatically. And increasingly, we will use various forms of AI also to get into the ballpark in the first place. But, this notion that we're at the end of a cycle, on one hand may be true for the amount that you ultimately can put on one monolithic chip. But again, there's still 10 years. But the combination of those, I think, is open-ended to enormous opportunities.
Yeah. Fascinating times. Well, we're at time. We greatly appreciate you coming on. It's been extremely insightful. I know everybody listening will value, and like I said, your insights have been enormously interesting. So we greatly appreciate you coming on our show.
Well, thanks a lot for having me. Ben, Jay, great questions were stimulating to me as well. So I appreciate that.
Thank you. And everyone, thanks for listening, and we will catch up with you next time.
Thank you, everybody. Thanks, Art.